Hello and welcome to my talk on revised taxonomy of steganography embedding patterns. This is joint work with 11 authors. I'm happy to speak on behalf of them and present our joint work here. So let me first give you a brief introduction on hiding patterns. The idea is that hiding patterns describe the key idea of hiding techniques of network covert channels originally in an abstract, non-detailed level, and they help up cleaning terminology and taxonomy. Well, so the original idea was that we take all the hiding techniques that we can find, back then limited to the domain of network steganography, and in the first paper we analyzed 109 hiding techniques published since 1987, and we could describe the core ideas using only 11 patterns. Later, more and more hiding techniques were incorporated, and right now we have approximately 20 hiding patterns. The advantage of these hiding patterns are that they help up cleaning up the inconsistent terminology because there were scientific reinventions. So that means some people just published the same idea using different terminology. So because patterns can be derived from each other, they can form taxonomies, and this is a big advantage for us. Like this. So this was the first patterns taxonomy, hiding patterns taxonomy for network steganography or network covert channels. So as you can see, we have the classical different distinction between timing and storage channels, and we have 4 timing patterns, and we have differentiated here the storage channels into those that modify payload and non-payload, where the modification of payload is mostly digital media steganography and thus out of scope in the original taxonomy. And the non-payload, that means headers, all the metadata and padding fields are differentiated in those methods that modify the structure of, for instance, a network packet, or that preserve the structure of a network packet. As you can see, there are also child patterns feasible because we can derive them. In later versions, we extended the taxonomy. So this is what you see at the right side. Here's the latest version, and top are the timing, and below the storage channel patterns. And some additional layers were added, like protocol agnostic and protocol aware distinction. And for user data, there's also distinction. So this is state-of-the-art 2021. However, the current taxonomy has some limitations, and these limitations are especially the following. So first of all, we have a focus limited on network communications, so we neglect other domains of steganography like text or digital media steganography, and of course we want to include this. So this is one of the major contributions of the new work because we want to address this problem. And the level of abstraction does not easily allow for inclusion of non-network patterns because, for instance, in this taxonomy, we speak of payload. And so while digital media steganography would entirely end up here in the payload domain, from the network steganography perspective, we also want to apply timing considerations for digital media steganography, just to give an example why this cannot be easily integrated. Another big advantage actually a limitation of the existing and advantage of the new taxonomy is that there is no distinction between the embedding and representation of hidden information. Which renders the pattern taxonomy in its recent form a little bit ambiguous. And some patterns must actually be described as hybrid patterns because they are a combination of embedding and representation pattern. However, we kept lots of key concepts from the previous work. Several aspects were functioning very well. We kept even many names and some distinctions that we had previously. However, the new taxonomy is more abstract. What is our approach? So first of all, as mentioned, we distinguish between embedding and representation patterns. And the embedding patterns describe how secret information is in fact embedded into the cover objects, such as a file, image file, audio file, or network packet. And the representation patterns describe how the secret information is then represented in that object. And in fact, both can differ. So while in many cases it's the same, for instance, if you just modify the least significant bit of a protocol header field, then you apply and read out the same information from the same location with the same methods. But especially for indirect patterns, this can be different. Secondly, we applied a more systematic naming convention. Therefore, we first of all changed pattern names in a way that they, in many cases, the original concept of the network hiding patterns, also for backwards compatibility, was kept, but we need to rename them. So inter-packet times modulation became event element interval modulation. So we have the interval between some events that occur, for instance, and we modulate these intervals. Message timing is also too specific. So in the end, it's events and it's not their timing, but in very generic terms, it's occurrence. We removed some aspects like payload and protocol awareness. And we also removed the differentiation between syntax and semantics. Have a look at our paper for a discussion on this. I will skip it for time reasons. Then there are there's a definition of how pattern names must be must look like. So they contain identifier and a name, and the identifier follows some structured format where the first letter tells us whether it's an embedding or representation pattern, and then the next letter tells us whether it's a temporal or non-temporal pattern. Then it has some number, and optionally, but only for the representation patterns so far, it has a domain indicator. If it's specific to network steganography, it would be a lowercase n, for text stego a lowercase t, and so on. So pattern identifier would look like this, RT1T. We then, to describe the name, we add to the identifier a modifiable object, for instance, an event or feature. The list of objects is here, and an action. So what do? We modulate, or something occurs, or there's some positioning. And as you can see in this table, when we exemplify the objects over different domains, so we have different contexts here, then for instance, the interval object would be for network steganography the time between packets, for text steganography the time between text node send, and for digital media it could be duration of an audio file, while this is scaled down to the state or value of features that are specific to elements and that are specific to events. So for instance, a state or value could be a value in a header field, number of packets, number of characters in text, and value of a pixel or number of pixels in an image. All right, so the major contribution here so far is the embedding taxonomy. The representation patterns are in this paper only exemplified for the network steganography domain, and follow-up work will extend this to more domains. However, let's look at the embedding patterns. So we differentiated between temporal and non-temporal behavior here. So all hiding patterns, as you can see, are either embedding or representation patterns. We will look at the representation patterns in a couple of minutes. So first, however, let's look at temporal patterns. I won't cover the sub-patterns that are in light blue color here, also for time reasons, but they are described in the paper. So the first pattern is the event element interval modulation, and there the covered message is embedded by modulating the gaps between succeeding elements or events like network packets, where we can modulate the timing between packets that we send, but we can also apply this to physical systems and other Steger domains. So in the paper, we provide usually 3 examples, and they cover different Steger domains to exemplify this in a broader context. For the second timing pattern or temporal pattern, the event occurrence pattern, we modulate the temporal behavior in a way that we encode hidden information in the temporal location of events. And that means that we do something at some specific time, for instance, sending a specific network packet at 6 p.m. or influencing the time where a drone starts or performing a disconnect at some point in time. Now let's look at the non-temporal patterns here on the right side. So first of all, there's artificial element loss modulation. That just means that we embed the secret information by modulating some artificial loss of elements. For instance, we could artificially drop TCP segments to mimic a reliability feature and saturation. And we could also remove commas in sentences. For the second pattern, elements features positioning, the covered message would be embedded by modulating the position of a predefined set of elements or features in a sequence of elements or features. Sounds difficult, but actually the idea is pretty simple. So look at this example below. We could modulate the order in which these header lines appear. So first user agent or first accept language line, or we could place a specific character in some paragraph. The elements features enumeration pattern works in a way that the covered message is embedded by altering the overall number of appearances of elements or features. So we count their number in some sequence. So for instance, we could fragment a packet in either N or M packets. We could modulate the number of people wearing a t-shirt in a specific color in an image file. Or we could repeat an element or feature by duplicating some white space character in a text. For the state or value modulation, here the covered message is embedded by, well, modulating the state or the value of such a feature. And examples are that we could modulate some physical states like proximity, visibility, height, acceleration, things like that, to embed the hidden information into this state. Works, of course, also with several header fields and network packets, or with coordinates of a player in a 3D game. And finally, the feature structure modulation pattern. So we alter the structure of the feature that we utilize for embedding, and that encodes hidden information. For instance, we could increase the size of network packets so that we have either size 1 or size 2, so signal hidden symbol 1 or 2. We could also change the color or style of characters in text. Now let's have a brief look into the network steganography representation pattern. So how would the information be represented for the covered receiver? So what is it that the covered receiver needs to look at? And these patterns are derived from the embedding patterns. That's a key thing. So we do not reinvent the wheel here. Let's zoom in on the representation patterns. And as you can see here, in non-bold font, they are derived from the embedding patterns ET1 and so on. And this also works for the sub-patterns. However, there are some specific patterns that are derived in the domain-specific context. For instance, this RT2N pattern, frame corruption, comes from the original frame corruption pattern that was already present, is a special version of the event occurrence pattern. So there's some event, but it's a corrupted frame, and it's described multiple times in the literature. So it's a pattern for the network context. And this is why we add an N here in the end. We have 2 more, the artificial forced reconnections modulation. So the artificial loss here is a network connection, and we force a reconnect. And the same goes for artificial retransmissions, also specific here for the network context. Conclusions and future work. we revised the existing hiding patterns taxonomy, and we addressed several of the limitations. These limitations are especially seen from the perspective of applying the patterns taxonomy to the whole steganography domain, which was never the intention of the original taxonomy. It's very specific to network and steganography. We addressed also other limitations, like the fact that there was no distinction between embedding and representation process. So we made the taxonomy more generic. We can use it for also CPS steganography, text steganography, file system steganography, and so on, and follow-up work will show this. We kept the good concepts of the existing taxonomy and incorporated them. So we did not reinvent the wheel, and we tried to achieve as much backwards compatibility to the existing taxonomy as feasible, because we do not want to break the understanding and the consistency of the literature if not necessary. And we have shown the first representation patterns for the domain of network steganography here. In future work, we want to show the representation patterns taxonomies for other stego domains like CPS or file system, digital media and text steganography. And we consider, but we are not sure right now whether it will work, extend the size of the consortium to integrate also the domain of digital watermarking. So if you are interested in contributing, especially this aspect, then let me know, and I will bring you in touch with the whole consortium so that we can discuss this. All right, there's a website where we explain again all the details, and I thank you very much for your kind attention, and I'm happy to answer your questions now.